Here you are. Oops. Hey. Great question. We're going to cover in this deep dive what it means for a system to be deterministic, non-deterministic, and stochastic, and talk about these at a general level, and then talk about them in terms of AI. And then we're going to get into the importance of understanding the difference between traditional hacks to software and AI takeover. And then probably a bunch of other meandering stuff. So we're not going to start for another 15 minutes. And great to have you from Australia. We're in Australia, by the way, JV. So feel free to cyber pandemics. Wow. Quail, that's a great question. I have a lot of thoughts about that. And I think that we're on the breach of a major cyber pandemic based on stuff that's going on with stochastic AIs. Sydney, sweet. I've been to Sydney once, JV. Absolutely loved it. Only for just like a couple days, but yeah, absolutely love Australia. Spent a couple weeks in Brisbane, Australia, and then a week in Melbourne, Australia. But for me personally, I like Brisbane more than Melbourne. Yeah, cool. Yeah, feel free, guys, to go grab your soda, your food, your popcorn, all that stuff. And we're going to start probably in 15 minutes or so. I'm going to assemble the crew. And by the way, this may be a long one. We might be going for a while because I want to really get at the heart of some of these things and discuss the difference between language models. Let's see, language models, world models, and like knowledge graphs. Knowledge graphs, as well as just general semantics reasoning. And a lot of this is inspired by the hack that we recently saw on X with Grok. And part of that is I was getting some feedback with people being confused on like, well, what does it all mean? And so I'm going to try to explain some of this in a bit more detail. I'm going to have to shrink this down a little bit. Yeah, here, let's do, okay, that'll probably work. So yeah, super pumped. Glad to have everybody here. Hey, brother. The source today is really us just continuing to dig in to the fundamentals of AI. we'll probably meander, but we're going to talk about this stuff. Oh, you guys can't see that. Uh, I'll get into it, but basically we're going to go over fundamentals of AI and help everybody try to understand the difference between language models and then some of the stuff that I'm proposing and other folks that are trying to build out the AIs that will like actually work, like Jan LeCun with world models. And now, before I forget, let me inform the Discord. Uh, cool. Alrighty. That usually gets people fired up right away. And for those of you that aren't on the Discord, you're welcome to join. No pressure, but lots of awesome people over there. And totally free. Lots of discussions. And also, it has a lot of our coupon codes for various partnerships we have that you can basically get the discount codes for stuff that you may or may not be interested in. Okay, hold on. What's this? Okay. Uh, cool. They're trying to help each other out. Excellent. Okay, looks like some of the folks from Discord are rolling in to YouTube. And for those of you that are on IG, I'm going to try to make this IG friendly. What I'm probably going to do is move OneNote over the portrait here so you can see. Here, let me show you what I'm talking about. I'm probably going to center OneNote so you can kind of see this and follow the various things. But you may get a more holistic experience if you hop on over to YouTube. If you can. I know that some people can't. They need to just be on their phone, and that's totally fine. Just do whatever you can. And then also keep in mind that these are all recorded, and they go on YouTube in low fidelity form, and then I put them in the members section, high fidelity, as soon as I finish. So essentially you can get them in a bunch of different ways if you only get like the narrow screen. I'm going to try something real quick here. Source projector, new window. Cool. Okay. Let's see. putting a mini window of me behind the modal window of me so I can see myself a little bit easier here. All right. Cool. I feel like I'm forgetting to do something here. We've got the mic going. We've got the live stuff going on a bunch of places. All right, it's slightly early. Hey, Clayton. Good to have you. What am I missing here? Hey, Dale. What's up, brother? Yeah, I could bring up some slides. Yeah, we might look at slides. Have you ever attempted to make your own LLM model that will be up there with Claude or OpenAI? Not yet, Clayton, but we have done some fine-tuning and refinement of small language models. And the moment that we kind of get diff stabilized, depending on what our investor situation looks like, I think that there is a chance that we could do this. Yep, I hear you, Dale. So I wouldn't rule it out. I will say that we're very determined to create our own small language model, since we think that that's necessary. And I'm really keen on small language models just to kind of have distribution of power and stuff. But I also realize that language models are, you know, hyper effective and, oh, yeah. So just to be clear, for any of the IGers, you guys are probably seeing just the portrait mode, which shows you just a small section of my whole screen. If you jump over to YouTube, let me drop the link, you'll see the whole screen. Me. And I think for most people, if you turn your phone sideways, you can see, you can kind of get like a 16 by 9 type of dealie. I think. Maybe. The biggest hurdle, Clayton, honestly, is the financial resources that are required to train the models. That in order to sufficiently train a large language model, the data part is actually not that hard. But yeah, having the data center compute and being able to cover, because it'll cost on the order of 10 million to $100 million to, well, maybe 100 million's a little too large. Let's say 10 to 30 million dollars to train a large language model that is kind of on par with Claude, OpenAI, and all the kind of bigwigs. But then when you combine diff with our potential LLM, then you're likely going to get fidelity results, essentially accuracy and richness that you wouldn't get just from a language model, which I have somewhere in my slides. Yeah, Matt, so I actually have some music rocking for me in the background. Maybe I can bring some up for you guys. Hold on, what does my timer says? My timer says I'm expecting like a delivery that's going to have some perishables in it, and I want to kind of grab that before we really dive in, just so it's got my my doggy's food, and I don't want it to accidentally sit out there. Uh, Hold on, let's change this. Once funded, ballpark to train. Once we have the infrastructure, like the topology in place, 2 to 3 weeks. Probably to get 2 to 3 weeks to get the baseline model, another 2 to 3 weeks to refine it to where it's pretty competitive. And yeah, so if we're being a little conservative, 2 to 3 months for us to have basically an LLM that could be, I think, competitive with OpenAI, Anthropic, all the, yeah, Google. But one of the things that makes us in a unique position that edges out many of the AI companies that are just using language models or using traditional types of formal verification is they don't have diff. And diff is like a superpower. So diff by itself is pretty cool, but diff combined with a language model is pretty, it unlocks a lot of things. I wonder if there's an analogy I can use here. It's kind of like hybrid vehicles. So if you have a petroleum-based car, you know, it can get you places, but gas costs money, and it's also not great for the environment. But then if you have a full electric car, like that's cool, but you can't necessarily travel long distances. But if you have a hybrid, well, now you kind of have like the best of both worlds. And that can let you do a whole bunch of stuff that you wouldn't be able to do otherwise. Yeah. Yeah, and part of that, Clayton, is just that the the group that we have in GTT and in Merle, a lot of us are like pretty seasoned in this space, as well as the folks like my students at the uni and my academic colleagues at the uni. We know this stuff pretty well, so it's not like we're coming in fresh. Where a lot of the startups are, you know, they're kind of maybe they're familiar with the tools that exist, but maybe they don't understand a lot of the theoretical underpinnings. And the reason why that matters is if you know the tools, that can get you off to like a good start in terms of building something. But if you don't understand like the theoretical foundations of things, you could be heading down a wrong path for a very long time before you realize that it's like, uh-oh, that path is a dead end. Whereas if you get the, hey, Neon, what's going on? Haven't seen you in a while. Hey, Willie, what's going on, brother? Great to have you. And Dale, thanks so much, man. I appreciate that. Uh, I I appreciate the love on the YouTube members. And for all you YouTube members, you basically get all the live streams at high quality, 0 ads, which, at least for me, that's like the price of admission. And then again, once we get to over 100 members, then I'm going to start doing some like pretty far out member only VODs. I won't do it too frequently because I still want to make the majority of the content available to everybody. But once in a while, when I really want to lean in on something, I will do that. Oh, yeah. No, Dale, I love you, man. You're awesome. I think you've got a lot of great ideas and love your energy. Yep. And I'm glad we got through our little snafu. You know, this is just typical growing pains, as far as I'm concerned. Okay, let's see. We've got if it costs that much to train LMs, how come there are such good smaller ones that are just... Yeah, so the reason for that, Yara, is... So the great question. The SLMs are often going to be orders of magnitude smaller. And when they're... Cool. My delivery is going to be landing here shortly. So they're going to be orders of magnitude smaller. And so we're talking about 10x, 100x, 1000x smaller. And each time you reduce one of those, the size by an order of magnitude, the price of the training also drops by an order of magnitude. So if it costs, let's say, 10 million to train an LLM, and then we drop 2 orders of magnitude for an SLM, well, now you can train an SLM for 100 grand, right? Now, the big trade-off is SLMs, brother, yo, yeah, seriously. I wish I could heart these things on Insta or any of them through Restream. So the trade-off, though, Yara, is with the SLMs, they are domain-specific. So you lose the general purposeness that you would get from an LLM. But the truth is, as many of you guys probably know, most of the LLMs are actually an ensemble of models. And there is like a front end, I mean, based on what I know. Now, I'm not the knower of all things. By the way, we're going to get into some really complicated stuff here, and I'm not going to get this exactly right. So I want to first start by saying I am not the knower of all things, and because I'm going to try to cover like 10 different domains, I know I'm not going to get all this right, so I want to apologize in advance for mistakes that I make. I'll try to correct them in the VOD version, like I did for the DRB cryptocurrency. I kept calling it DBR, but it's DRB, Digimon Rabbit, I believe. But just know that because we're going to cover so many different things, I'm only human, and even though I've been studying this stuff for a while, it's difficult for me to keep it cached into my head at all times. But we're literally going to get into minimally machine learning things. We're going to get into systems. We'll get into programming languages. We'll get into software engineering. We will get into formal methods. And we will discuss like fundamental properties of algorithms. Things like P versus NP versus NP complete versus NP hard. All of these things, because those things have foundations in these things. Determinism, non-determinism, stochasticity. And these are all uniquely different things that oftentimes I think there's some confusion about this stuff. So anyway, Vihan, that's great. Great to hear that we've got Sri Lanka in the house. It's fantastic. I've never been, but it looks beautiful from what I've seen. Like, at least the photos I've seen, like, very lush. Awesome. Uh, I've developed a message bus that outpaces GPU on speed latency. Awesome. Yeah, Dale, I think that you're cooking some major things up. Why Clayton's got a whole bunch of great questions. So let me actually move this. Whoops. I just killed the. Hold on a second. Ma, where did the chat go? Oh, here it is. It attached itself. Hold on. I'm going to move this down here so you guys can see this. And then we'll bring OneNote back up. So now you guys can see this is the chat for YouTube, Kick, and Twitch. And then over here for IG, you've got this. By the way, we're starting to get people dialing in from TikTok, but I don't bring up the chat for TikTok. Maybe I will at some point. At some point, we need to figure out how to unify all the streams. So hopefully people will figure this out. And then we can just use their software. But right now, Restream will only unify YouTube, Kick, and Twitch, which is why we've got them all here. Anyway, Clayton's asking this great question. Why is Claude so much better at coding than the rest? I think that's for a few different reasons. Okay, let's pause this for a moment. And let me go grab my delivery thing. I'm going to do a quick bio and gather the stuff up, and then we'll start for real. So you guys probably have maybe 5 minutes or so, 5-7 minutes before I'm going to officially kick off. So feel free to run to the bathroom, grab a soda, all that stuff right now, so you don't miss the actual content. And hold on to that thought, Clayton. We'll circle back to that. Okay. Alrighty. I think we are ready-ish. And I can't tell if I... Where's the power button? Give me one. Here we go. Can't tell if I can see better with my glasses or without my glasses. I feel like, well, when I look like that, I can, but yeah, well, yeah, it's better. I don't know. My LASIK, I think, is settling, and so I think I'm starting to be able to see more clearly. Have any of you guys had LASIK? Just drop a 1 in the chat if you've had LASIK. And if it's normal for your vision to improve over a period of time rather than being kind of immediate. This is all new to me. I'm probably spending thousands of hours of Claude. I know he's based on the mathematician Claude Shannon. And so it might be able to do with his ability to crunch numbers. Yeah. Most AIs are trying to parse. Yeah. Yeah, there's many reasons why the Claude stuff is significantly better, but I think at the crux of it, one, the founders of Anthropic were former OpenAI folks, and so they already had a bunch of experience of kind of dabbling. I think Dario was maybe their chief scientist. I'm not entirely sure about that, but one of the things that I think Dario did right is he pulled in a bunch of really smart people, like hyper, hardcore PhD professor. Not that you need a PhD or to be a professor, but like people that are very seasoned in machine learning, and then gave them the ability to build the stuff kind of the right way and from scratch after already having a bunch of experience kind of dealing with this and seeing what didn't work. And I think that's one of the superpowers that Anthropic has, is that many of the other folks, they had a lot of legacy stuff. So I think that's part of the reason that's holding Google back and Amazon, is there's a lot of this legacy stuff that maybe wasn't perfectly right, and trying to reuse that stuff because it seems at first that that's the more effective way, but then it turns out maybe not so much. Anyway, there's a bunch of other reasons, but maybe we'll get into that later. Okay. So for this live stream, I'm probably going to be in a little bit more scientist professor mode than I am normally, because we need to go over a lot of precise scientific terms and definitions for all of this to make sense. What I'm going to try to do is draw a bunch of pictures the whole time. So if any of the words get confusing, like as we talk about things like non-deterministic polynomial or multi-head attention, things of that nature, that we have pictures that go with them to kind of explain what these things mean. But it's easier for me to explain a lot of this stuff using kind of the precise scientific things. I can just kind of think faster that way, so then I don't have to do like an additional one or two translations. But and the reason for that is I want to try to get at the heart of, one, why traditional hacks and AI takeover are so fundamentally different, and also to help try to explain what a deterministic system is, what non-determinism is, what stochasticity is, and how they're all kind of different from each other in sort of formal and somewhat rigid terms. And then I'll double back on it and then explain it maybe in easier terms. So just a heads up about that, because as I was on my run with the doggy earlier, I was thinking about how I would explain this stuff, and there's just a bunch of things that we may have to start with kind of like the formal language. Okay. And the higher order bit of this live stream is, one, to explain what it means to have a deterministic AI and what it means to have a stochastic AI. Also, why all language models are stochastic AIs, even if you see that inference is behaving in a deterministic way, and why inference behaving deterministically is not sufficient for the forward progress of the science. And then to get into the fundamental divergent paths of software that we've built in the past that is essentially from formal systems, since software code, like in programming languages, is semi to fully formal, as much as that may be kind of like a new concept for people. Like developers oftentimes don't necessarily think of the software code that they're writing as being like a formal system, but it actually is. And I can explain why it's a formal system. And that's actually very important, because stochastic AIs are not formal systems. And that's part of the big difference in capabilities between traditional software hacks and the potential dangers of AI takeover. And it's a fundamental reason why AI takeover is significantly more powerful and likely to cause a lot more damage. Okay. And feel free to ask any questions, like clarifying questions. I'll try to pause every 30, 45 minutes or so to run through the chat or to have us take a break. But with all that said, I think we can dive in and just get started. Okay, the first thing for us to start talking about, again, as kind of maybe strange as it is as a starting point for AI, is to talk about P and NP problems. All right, so we're going to bring this down here. And if you aren't familiar with what P and NP problems are, don't worry. It's going to be pretty easy for us to explain this at a very high level. And then the good news is, if you're computer science, then I think this will help you kind of understand conceptually why this is such an important thing, and why a lot of people are super concerned with this whole P being not equal to NP and all of this mumbo jumbo. All right. The key idea here is that when we talk about P-class problems, we're talking about things that are polynomial. We'll just write this down. And we talk about NP problems, we're saying that they are non-deterministic polynomial. And we've already gotten to the word non-determinism, which is why we started here. So what does this mean? All right. All of you probably had taken algebra at some point if you're watching GTT, and you remember things like x is equal to y squared, or x is equal to y squared times z times something else, and whatever, right? That's what polynomials are. So polynomials are basically just these expressions where you can capture the idea of the equation. And in this particular case, what we're talking about with these P or NP problems is all we care about is how fast they can be solved. That's the whole point of P versus NP. And when a problem is shown to be in the problem space of P, it's polynomial, it basically, all that means is we have the equation that we can use every time, and it will get us the correct answer. And it's known to be in polynomial time. So that equation we were just talking about, all that stuff, is that we know what that looks like, and we can say, I can guarantee you that no matter what setup you have for this problem, like it's a traveling salesman problem, or it's a massive search, or whatever it is, walking through all of the grocery stores in San Jose, right? Those are all various types of problems that you would want to solve with this type of computational time complexity. And when it's P, it basically just means that we know that it's guaranteed for all cases that we know what the upper bound of time is. And it's growing at this, essentially this fixed rate. That's the cornerstone idea. So let's read what this says. So a polynomial time, problems that can be solved quickly by a computer where the solving time grows at a reasonable rate as the input size increases. And reasonable is, who knows what that is, but it's not something necessarily that is like n to the m to the q power, right? That would be a computational explosion, and that's not polynomial time. So let me back up. I think the more scientifically precise definition of the polynomial stuff is that each of the polynomials are essentially a fixed number. So it's something like, and again, I haven't looked at this stuff in a very long time, so I might be getting this not exactly right. But when I say x is equal to y to, y squared times z cubed, the point is that those exponents are known, and they're reasonably small. So, but it's not x is equal to y to the z power, this kind of thing. So I believe that there's something about they have to be constants. All right. That's basically all you really need to know about the P problems. Is when we're talking about these classes of problems, it's all we really care about is just how fast we can solve them, but we have to be able to solve them for any input. This basically has to work for all the inputs. So you can come up with all these strange corner cases, and it still needs to be fixed in polynomial time. An example of that is like traveling salesman, is that no matter how you construct the graph and where you put the salesperson in the graph, like it's known to be or maybe it's known, I can't actually remember, but maybe it's known to be polynomial time, right? Dijkstra's shortest distance, something or other. All right. Now that gets us to NP. And NP, the most important thing to know about this is just this piece. It's non-deterministic, which makes it in this potentially other space than P. So the only difference between these two classes, this one's polynomial, this one's also polynomial, but it just has this one word in front of it, non-deterministic, which, again, going back to the things we're talking about, is this thing. Trust me, this is all going to make sense in just a second. So we read what this says: problems that are where a proposed solution can be verified quickly. Okay, yeah, so there starts to get these breakdowns of different categories. So it's like NP, NP hard, NP complete. But so the proposed solution can be verified, but the actual solution, I think, is still potentially non-deterministic. Yeah, so even if finding the solution itself is hard. And those details, we don't need to worry about those details for what we're talking about, but just know that the step up in computational complexity, it starts with P being the base level of, like, this is kind of the lowest space. And then one step up is non-deterministic polynomial time. It's like, okay, this is a little bit harder. Harder meaning it's going to take more time to kind of figure this stuff out. And then as you go deeper down, you get into NP complete. And I feel like there's NP hard in here, but I don't know where that is. Anyway, so NP complete, the hardest problems in NP. If any single NP complete problem is solved in polynomial time, then P is equal to NP, yada yada. But oh yeah, look, they're even talking about traveling salesmen. So yeah, I don't actually care about this. I actually want, like, the definitions of this piece. Okay, hold on. We need to go, like, a little bit further. And I really want to rely on the internet to say this just so I don't accidentally misrepresent it. Okay, yes, so we're talking about the complexity class. They can be solved by a computer. It's all about time complexity. And yeah, so here's, oh, see, here's your NP hard thing. Right, so here's your space of P. This is basically, like, this is the easiest of all of them, and we really want to be here. And then there's, like, the space of NP, which has this non-deterministic piece. Key thing, just keep that non-deterministic piece in your head. And then the NP complete, which this is, I believe that it's both non-deterministic polynomial in the solution and also in the verifier. Or maybe that's NP hard. But the point is that as you go further down this rabbit hole and you get into the deeper time complexity of these problems, it takes more time. All right. Now, the big takeaway here, the most important piece of all of this, is that this is essentially the built-in nomenclature in the scientific community. And so when we use the word non-determinism, we tend to mean non-deterministic in time, not in outcome. So the idea here is that these solutions that you're going to propose to these problems, they're going to get the answer. You just don't know when they're going to get the answer, but they're all going to get the answer, and it's going to be the right answer. And so the non-deterministic piece here simply means we don't know when this is going to complete, but we do know when this is going to complete. Okay, Now let's go back to AI. You'll often hear that I talk about you can have deterministic AIs and you can have stochastic AIs. The reason why I classify these in these two different categories is I'm not really that concerned about the time window, the latency of inference. That it is definitely something that is non-deterministic based on whatever AI system you're using, like the data center it's using, the number of nodes in the cluster, all these things. It's going to make the latency, that time component non-deterministic, but I don't really care that much about that piece because I know that if it's a deterministic AI or if it's a non-deterministic AI, it's still going to come up with the same answer. It'll just take a different amount of time. But a stochastic AI is saying that I won't even guarantee you that I will come up with a consistent answer. And that's why language models are not non-deterministic AIs, they are stochastic AIs. Because when you ask a language model to give you an answer, yes, it is potentially non-deterministic in its latency, but the bigger thing is when you ask it 1 + 1 is equal to what, it might tell you 2, but it might tell you 4087. You don't know because it is a stochastic system. And diff, on the other hand, or other formal solvers or other AI systems that are deterministic, like linear or logistic regression, those are deterministic AIs, and they will always give you a deterministic answer. So let's just look at the definition of stochasticity at a high level. Stochasticity refers to property of system, process, or model that involves random, unpredictable variation. That's exactly what we're talking about here. We're talking about random, unpredictable variation. That's what language models do. This is why language models are not non-deterministic AIs. They are stochastic AIs. And the truth is, between different language models or even different implementations of diff, you might have non-determinism in the time window, but you will have determinism in the output. Okay, so let me take a pause now that we explained this is the cornerstone, the starting point of this discussion, and hopefully this clarifies now a little bit more on the distinction between a deterministic AI and a stochastic AI. And we're going to go a little bit deeper into this stochasticity because right now you may have heard me say this thing. It's non-deterministic in its latency, but it's deterministic in its output. And stochastic AIs are, I don't really care that much about their latency, but they are going to be unpredictable with their output. And we're going to get deeper into the differences between inference and training, or what I refer to as refinition, and why some of you may be saying in your head, well, Goju, you just turn the temperature to 0 and then everything's fine. I'm not actually really thinking about inference. I'm thinking about training, because the bigger concern here is not about the answers that users get. It has to do with being able to reliably advance the science, reliably advance the language models. And that part is stochastic. So no matter what you do with inference, let's say that you convince me that inference can be made deterministic. Okay, cool. But you can't make refinition of neural networks anything but stochastic, which basically means they're going to lose the property of being reliably, iteratively refinable, which is a major, major problem. That is the crux of the problem right there. Well, yeah, and that they don't have semantic understanding of things. So let me take a quick pause. Hey, JB, and just see if there are any like clarifying questions about this whole P, NP thing that we just went over, the polynomial, the non-deterministic polynomial, how that relates to the time complexity, and how that then influences the words we use when we talk about these AI systems, and why I never really talk about non-deterministic AIs, because this word is reserved in computer science and in mathematics to refer to temporal windows. It's non-deterministic in latency. It's not non-deterministic in output. That word is stochastic. That's stochasticity. Okay, cool. I'm gonna puff on my vape for a second here and see if you guys have any like burning questions, or if I'm putting everybody to sleep. Just think if you had to listen to this actually in person in one of my lectures. And I require that all the students put all their phones away. I mean, I kind of do, but I don't actually really enforce that. Is the series going to be hosted anywhere like YouTube? Yes. Brooklyn Bartender, yeah, we have a YouTube channel, and basically all the live streams are available there. So you can get I just dropped the link. You can get the recorded live stream from YouTube literally the moment that it finishes, or as it's happening. But then I do an upgrade of the production quality afterwards, and then for any of the YouTube members, they get essentially a crisper, higher quality version of the live stream with no ads. So, but basically all the live streams that we've done, I think, oh, that's not true. I think I wiped them at one point. But most of the live streams now, I leave on the YouTube. And Brooklyn Bartender, if you would like a full immersive experience, you may want to hop over to YouTube, because you'll be able to see like all the things that are on my screen. Or you can stay in IG and you'll kind of see the portrait mode. Okay, so awesome, Yara, not putting me to sleep, trying to see how much of this overclocking I'm capable before the smoke comes out of my ear. Yeah, and I apologize for all the scientific mumbo jumbo, but hopefully you can kind of understand now why I needed to send us down this path, and why I will constantly talk about stochastic AIs, and I really never talk about non-deterministic AIs, because I kind of don't really care that much. Okay, JB's got a question. Let me pull this over just so all of the IGers can see some of the stuff that's going on, and TikTokers. For a deterministic AI, would its weights need to be fine-tuned, updated regularly, or will it be doomed to be non-generalist by definition? Yeah, I think that it depends. To the best of my knowledge, any neural network, doesn't even have to be a language model. It could be a long short-term memory, or it could be a convolutional neural network, or a Hopsfield network. Anything any type of neural network, all of them are stochastic. And the reason for that is you must randomly initialize the weights of neural networks in order to get high probabilities of convergence on their definition. So that basically means that it is impossible, essentially impossible, to make a neural network deterministic. It can't be done. If you initialize those weights to non-random numbers, that is no longer a neural network. So you have something else. I'm not sure what that is that you have, but it's not a neural network. And part of the reason why that's so important is that stochasticity is part of how the learning algorithms work. It's actually because of that randomness that they're able to converge on things. It's sort of like that's a property they require to function correctly. Now, if you go outside of just neural networks, so if you go to other machine learning techniques like diff or support vector machines or Bayesian networks or any of this stuff, isolation forests, then in those cases, it kind of depends, right? Like, so for example, diff is fully deterministic and can learn on things, and it guarantees determinism in its definition. And then from there, you can guarantee determinism in inference. But one example that I think is kind of interesting and unusual is k-nearest neighbor, or k-means clustering. So k-means clustering is also a machine learning technique, but the way that it works is the sampling size of KNN is random. And because of that randomness, that system itself is stochastic. But it's only one random number, essentially. So you could burn that in, and it does lose some convergence properties if you burn that number in, right? Because basically that random number is going to be based on the size of the clusters that you think are going to be present, and it does some like analysis of the sample data at first to kind of figure this out and speculate on it. But that would be an example of an ML system that you could probably make deterministic without massively losing convergence properties. What I would do to make like KNN deterministic is I would have buckets of sizes. And so if it's 1 to 10 in a cluster, that would be one size, and I would fix the number. And then if it's like 11 to 100, I would fix the number. And then 101 to like 1,000, it would be another number. And then because of that, you could actually make KNN deterministic. It's probably not going to be as wonderful as KNN when it's stochastic. But because it has this deterministic seed, then you can rely on that for iterative refinement. And so on and so forth. And you can do similar things, I think, with, I can't remember if support vector machines off the top of my head are stochastic or not. I think they don't need to be. Yeah. So hold on, let's circle back to this in a second. Awesome, Brooklyn. Yeah, man. Great to have you here, and thanks for joining. Okay. Oh, okay. I think I. Hey, thanks, Yara. Okay, I think I'm starting to understand what you're asking a little bit more clearly now, JB. Let me try to reprocess this. So for a deterministic AI, would its weights need to be fine-tuned, updated regularly? It would be doomed to non-generalists by definition. By weights, I mean the deterministic AI correlated equivalent of weights, if that makes sense. I think you're saying something pretty important here, but I don't think I'm fully grokking it. Mm. I'm not sure. I'm going to have to think about this. But I will say that there's something interesting I think you're teasing out, which is this notion of, does deterministic AI make it something that is like non-generalizable? And I don't think so. I think it fundamentally has to do with the way the systems learn, and that neural networks learn in a very particular way that it does require this pseudo randomness or this randomness, but other systems that can still absolutely generalize, like linear regression, they can do this in a fully deterministic way. And same thing with diff. Diff can absolutely generalize. Yeah, it can generalize just fine. It's just the way that the learning works, because the way that the learning works for neural networks is the way that I think about it. This goes back to the linear algebra component. Is you kind of just imagine a geometric space in your head where you've got like a topology. Like think of a map, and you have the mountains and you have the valleys and you've got all this stuff. That's a neural network. That's an easy way to kind of think about a neural network. And all the different peaks and valleys, those are the pseudo-random weights, essentially. That's sort of it. I mean, that combined with the data and the biases. So, in that case, because you've got all this kind of strangeness, what you have to do with the learning algorithm is you have to try to figure out how to find this global minima with all these weird peaks and valleys. And because you need to do this, the learning algorithm that you use, it functions with a lot higher degree of convergence if it's also stochastic, like stochastic gradient descent. So I realize that's a little bit of a mouthful. Let's just break it down. Stochastic gradient descent. It's stochastic, which means it's not going to be deterministic. It's a gradient. So a gradient is just a degree of change. It's not binary. And then descent is it's just going down. Stochastic gradient descent. That's all that means. And that's a type of learning that you have for neural networks. And that works very effectively for neural nets because of the randomness of the weights. Whereas if you use things like conjugate gradient descent or other fixed learning algorithms that aren't random, they don't have the same likelihood of convergence. Anyway, we could probably continue this on the Discord. Oh, speaking of which, let me just drop the Discord so we can get more Discordians. If you're enjoying this live stream and you like to nerd out, please hop on our Discord. It's totally free. There's a whole bunch of like-minded people that really like to talk about AI and technology, and you'll probably fit right in. So please check it out. Or don't. Okay. So actually, JB, let's put a pin in this conversation just for the moment. We can continue this on the Discord. But this is actually a really good segue to explain what I mean about the stochasticity of neural networks and why it's a fundamental problem. So I want to talk a little bit about Jan LeCun and his world models and our deterministic intent folding. And one of the, yeah, and we can continue. I actually think this is a really interesting conversation, GB. So, JB, I'm not trying to shut you down. It's just you're reminding me now. This was the next thing I want to talk about, and I want to make sure I explain this before I forget. So many of you have been probably hearing about Jan LeCun talking about these things called world models, and he's saying things. He'll say things like, language models are absolutely not going to work because they don't understand how the world works. Okay, so what does he actually mean by this? Well, what he means by this is very much like what we saw with the Grok $200,000 giveaway, right? That's I think almost exactly what he's trying to point out. And it's the same thing I'm trying to point out, is that because language models don't actually understand what they're doing, they can't not do the wrong thing. It's not intentional. It's just that they don't have a real understanding of the world. Now, Jan is keyed in on these world models, and that's cool. I'm happy for him. That's a very specific way of approaching this, but you don't have to approach it with world models. All you need are semantic reasoners. Now, inside of his world models, you probably have semantic reasoners, but they're a very specific thing that understands how to reason about the world, because he cares about the world, and he cares about he cares a lot about images and physical objects. And for me personally, I don't really care that much. I care a lot more about the virtual world. I care about software. And so I don't think that the AIs that we're building at Merly or the stuff that we're doing on GTT has to have an understanding of the world. So I would push back on him and say it's actually not necessary. I mean, if it has full understanding of the world, I think that's awesome. But you can still build AI systems that understand things, that just have semantic reasoning capabilities. Now, let me explain what I mean. Is in the, if you guys haven't seen the video on the $200,000 giveaway on Grok, it's somewhere in here. It's this one. It's 26 minutes long. And I strongly encourage all of you guys to check this out. I think it is a really important example of AI takeover, which we're going to get into in a second here. But if you haven't seen it yet, maybe stay on this live stream, but then afterwards add it to your queue and watch it this weekend or something. But the summary of this is what happened in that. Exactly. That's exactly my point, JB. So JB is essentially making the same conclusion that I'm making. It's not that world models aren't awesome. It's just that if we're working in the virtual world, we don't need all the physics stuff, because software doesn't Software doesn't need to understand the physics of the world to work. Software just needs to understand logic and the semantic meaning of things. And it's true that in order to work in the world and do stuff like with robots, that you would need, I think, an understanding of the world. But that's overkill. That there's a simpler solution that will work for a smaller subset, whereas Yon's solution is like it's trying to solve everything in the physical world. And what's really interesting is that I think part of the virtual world is covered by the physical world, but not all of it. There are actually gaps, I think, in understanding of the physical world, with understanding like the world models that are not necessarily covered by just thinking about the physical reality of things. An example of that is like social media, right? Social media doesn't exist in the physical world. It exists in a virtual world, but it has rules, and we have to obey those rules, but it's an entirely virtual thing. So there is some overlap with world models into things that are virtual. Like in the physical world, you probably have to follow logical things to make it work. For example, if you're trying to buy things at the grocery store, the first thing you need to do is like get to the grocery store. So you can't just buy things from the grocery store if you aren't there. I mean, okay, you can with like Uber Eats and stuff, but if you're trying to do it like in Jan's way, you actually have to go there. So the point is that that is like causal behaviors. One thing leads to another that then lets you do all of the stuff. Okay, but let's take a step back here and let's think about this Grok example. So in this Grok example, this user tricked the AI into giving $200,000 away. And I was saying the reason why it does this is that the language models don't understand what they're actually doing. And I want to be super clear that all you need really is a semantic understanding of a general concept that can be captured when you have semantic reasoners for this to work. And the concept in this particular case is the concept of giving. That's the concept. So I have something in my possession, and I'm going to give the thing that I have to someone else. That's a concept. Now, there are millions of different embodiments of the act of giving. I could give someone a couple dollars. I could give someone a diet soda. I could give them advice. I could give them my dog. I could give them my house, right? But what's really important to understand in the semantics of giving is it's this idea of at the highest level, the way that I'm thinking about, like in this X case, is it's a transfer of ownership. This person or this entity owns something, and they are then giving it, so this other person now owns this thing. Now, if Grok understood semantically this idea of giving, then when the user went to give it these instructions to transfer $200,000 to the person that's asking for it, Grok would then be able to reason and say, hold on, this is, and this gets back to what Jan LeCun is talking about like language models don't understand how the world works, right? This is, I mean, he's right. Like, this is an example of how the world works. But again, you don't need a world model for this. All you need is a semantic reasoner. You need to have a concrete definition of a concept The concept in this case is giving, and the concept of giving implies ownership. It applies minimally in order to give something that is owned by one entity and being given to another is you need three things. You need the first entity, you need the thing, and you need the second entity. So there's three requirements in order for the act of giving in this particular case to work. But you can formally define this. You can define this as essentially a mathematical and a logical operation, right? Then, once you define this, the act of giving, this concept, it generalizes. We can generalize it for anything. It doesn't have to be related to crypto. Now, for those of you that were on the live stream and I was getting like super annoyed with MSN, is they were missing the point. They were talking about financial systems and all of this other like instruction misinterpretation. It's like you're in outer space. You're missing the actual concept that is fundamentally broken here, which Jan and I and several others that are like working in the space of AI and ML are trying to get across, is that language models do not have a semantic understanding of things. And until they do, it doesn't matter how much hard coding you do for these individual cases. Like, sure, somebody is probably already patched Grok to where it's got some hard-coded list for all the cryptocurrency. By the way, this is totally stupid and wrong way to do this. It's like, and I can almost guarantee you that this is how they're doing it because it's just easy and it's lazy, but it doesn't work. And I'll explain to you like very quickly in 7 seconds, you'll understand why this doesn't work and why that solution that they probably already implemented is just waiting to be broken. So what they probably did is they have a list of all the cryptocurrencies and they have this command to transfer funds that's related to each of the cryptocurrencies, and they're making that action probably like forbidden for a Grok. And the reason why they would do it this way is it's super easy. Yes, so Moxie, 100%. You're 100% right here. I want to show what Moxie just said. Is he's saying giving and ownership can be two different things, and they can get ambiguous for code and reality. I absolutely agree with this. It gets much more complicated when you move into things like virtual reality versus physical reality, and so I appreciate you drawing attention to this, Moxie. My explanation was a bit of an oversimplification, but it actually draws out one of the core challenges, is that even though it's easy for me to say that all you need to have is a semantic understanding of the act of giving, and then the idea of ownership, and then the idea of entities, you can see how it actually is far more complex than that. Because the act of giving a possession that you have to someone else, and then the act of giving advice to someone, which maybe is also possession, but it's like different in that you still possess it. It's it's not mutually exclusive. It doesn't exist in singular form. It's like replicatable. And this is part of the reason why this is so hard, is that once you start getting into the deeper details, it's like you have to try to figure out how to handle all these cases. But that's basically what semantic reasoners and these formal solvers, and the truth is, code actually does. And just to be clear, I said maybe in the beginning that when you're writing code, you're actually building a formal system. You are. I mean, let me weaken that a little bit. You're building, in the strictest sense, you're building a formal system. In a less strict sense, you're building a semi-formal system. But the formality is you are giving precise instructions to a thing on exactly what to do to satisfy the criteria of this function or this class. And that's why software programs historically are deterministic. They're deterministic because we give them formal, precise instructions that they must execute in a serial or potentially concurrent way. Yes, I know, but let's just keep it simple and put parallel computing, distributed computing, all that stuff off to the side right now, because our heads are going to start to explode once we start pulling all these other things in. So let's just assume, for simplicity's sake, single-threaded programs that are executing only deterministic functions, not things like RAND or fuzzy logic, and then that provides a formal definition of something. That's actually what software is, at least software historically. But the future of software, especially with language models, are creating these types of systems. They are no longer formal definitions of things. They are stochastic systems. And with that stochasticity, it changes the entire range of what they can do and then what happens when you abuse them. So for example, and this is going to take a while to explain, but when you hack a system that is deterministic, it has very restricted privileges and well-known privileges and capabilities that are going to limit the things that it can do, or more specifically, it's going to control the entire range of things that are possible. That, for example, if you hack someone's computer that's not connected to a network, and that the application that you hack doesn't have administrator privileges, it just has user level privileges, then essentially the best that you can do, because it's formal and all these things are like fully understood, is you can manipulate the program itself and maybe data associated with it, but that's sort of it. That's kind of it in a nutshell. When you hack a stochastic system like these AIs, it becomes significantly bigger. There's many, many more things that you can do because the system itself is not bounded in the same way that the system that is deterministic and uses formal systems are bounded, right? So like if you hack the program that has these specific functions, then in this particular case, let's say that the only thing you can do is call the functions that have been formally defined. The part that is in its deterministic envelope. But when you hack a stochastic system, it's not bound to these rigid formal definitions. And so if you do it the right way, you can unlock potential that is orders of magnitude bigger than if you hack a deterministic system, which is what makes traditional software hacking and AI takeover fundamentally different concepts. Even though in both cases you're hacking a software system, the capability of what you can do when you hack a traditional deterministic or formally defined piece of software is going to be relegated just to the stuff that it has access to. But for AI takeover events, it can get absolutely wild. And part of that has to do with the fact that the AI itself can essentially, I mean, I don't want to go too overboard here, but not only can the AI do all the things that it was trained on, based on what we saw with the Grok example, you can inject new things that unlock new capabilities into the AI, which is very, very hard to do in this space over here. I'm not saying it's impossible. I'm just saying it's extremely hard to do. Whereas with the AI takeover, what this guy did is basically he said, look, I'm going to add this library so you have access to these new cryptocurrency commands and behaviors. And then he did it, and then suddenly Grok could do cryptocurrency manipulation. That behavior didn't exist until the user had it learn that behavior, right? Now, if you try to do that with traditional software, I mean, good luck, right? Because because of its rigidity, because of the formalness, you have to ensure that the thing that you're providing it perfectly matches with the formal structure that exists in that software program. So for example, if this is like a C++ program and you're trying to get it to learn how to do crypto manipulation, if you send it like a Java library and say integrate with this, it's going to be like, this is incompatible with me. But with the AI systems, because of their stochasticity, right, because of their kind of nebulousness and their ability to learn and be far more flexible, you can send it stuff and it can be like, sweet, I can figure out how to like quasi integrate the system. And that's exactly what we saw. Okay, so I kind of went down a little bit of a rabbit hole there. Let me take a step back and right, I was pointing that Moxie's, by the way, Moxie, if you're not on our Discord, we'd love to have you there. It's clear to me that you have a really deep level of insight on things, and so we would be honored to have you part of the GDT Discord, and the link is up above. Let me take a quick scan of some of the comments that I may have missed, and then we're going to take a short little break, and then we're going to get deeper and circle back into this really important point of language models, world models, and knowledge graphs, which essentially relate to semantic reasoning. And in essence, the way that JB explained it, and let me just draw this picture, is, I love Jan. I think that he's a super smart guy. And I think that he's absolutely right that language models are not going to work on their own to solve AI. It's not possible because they don't have reasoning capabilities. But I don't agree with Jan that it has to be a world model. And that's mostly just because I'm not saying he's wrong. I think for the stuff that Jan cares about, he's probably exactly right. It's just that I care about different things. I'm more interested in software and things that live in a virtual world than the physical world. So his world model stuff is probably like an analog to our diff stuff. Is that diff was designed to function in spaces that just require semantic reasoning, and they don't have to have all of this additional stuff. For example, like with physics, as JB was saying, right? Like diff for software, I don't need to understand how physics work, and that's a lot of overhead and weight to support if you don't need it. So what I'm trying to say is that, like, world models, the way I kind of think about it is, so here's kind of language models in this stochastic space. And there's like a ton of different stochastic AIs. LMs are one, K nearest neighbors another. I think even isolation for us, which I love, by the way. By the way, if you haven't learn about isolation for us and you're deeply interested in AI, I'm telling you, I reviewed a research paper for isolation for us a few years ago, and I had never heard of them before. I literally stopped in my tracks. This is a wildly powerful concept, and I encourage all of you to check it out or add it to your to-do list. That I'm now so compelled that I'm going to start building isolation for us into our future AI stuff, and they were only recently invented, like within the last 20 years or so. And keep in mind, neural networks have been around since the 1950s. So 20 years is, right, like transformers were invented. Well, the paper I think was published in 2018, but let's assume they were invented like 2016 or something before they actually published it. So transformers have been around for 10 years. Isolation for us maybe like 20 years. But most people, what I find is they're not familiar with them because they're a little bit on the fringe. But conceptually, they are insanely powerful. I fully anticipate that isolation for us are going to blow up and become a cornerstone for one-class classification or anomaly detection or any of that stuff with a very tight computational upper bound. So in non-science nerd speak, they're going to be hella fast. They're going to be real fast. Oh, awesome, Moxie. Yeah, it's great to have you then. Yeah, welcome. Okay, so here's your stochastic stuff, and they're very cool. Like, these guys are super great for things like creative ideation, rapid prototyping, like dialoguing, because that stochastic piece makes them unpredictable, right? This is often why I think humans get confused into thinking that the language models are alive, because they can say really interesting and unusual things that humans would, right? But that's just part of their stochasticity. I mean, at the end of the day, I'm not trying to make any claims on that I understand what consciousness is or sentience or any of that stuff. But what I can tell you definitively is that language models are just math and data. And sure, maybe humans are also math and data. Like, so just to be clear, I'm not trying to say that that we're somehow massively evolved over them, but they're not alive, is what I'm trying to say. For all the reasons I've mentioned, like lots of times. The big thing is that you can power them off and power them back on and everything's just fine. You can't do that with things that are alive. The moment that you power them off, right, you just do this, they don't come back. Or at least with enough time that's passed. Yeah, you can kind of think of it as like that. All right, so now in this deterministic space, you have other things. No. Let me back up. Sorry, I need to change this. I told you I would get some stuff wrong. This is, yeah, okay. We'll still say that this is stochastic. And no reasoning. And the word reasoning is very important. I want to be super clear. When I say the word reasoning, I mean something very specific. I mean a system that uses logic, or it can use logic to think about things. So, If we look up the definition of reasoning, it is the logical process of doing a whole bunch of stuff. Okay, let's not worry about all the details of all the things, especially not judgments, inferences, and all this stuff. But the key idea of reasoning is it's a logical process that is based off of knowledge, facts, or premises. We can just stop right there. Oh, and then form conclusions. But it doesn't even have to be conclusions. It can be assessments, like just trying to understand. The key thing about any reasoning system, and what I mean here in terms of reasoning is I mean this in a formal sense, like as a scientist, as a professor, as like the folks that are kind of like publishing peer-reviewed research. This word means something very particular. So when we talk about things like symbolic reasoners, what we mean is that is a logical system that uses symbols to think about things. That's kind of the essence of it. So you literally have, and then you'll also hear about, sometimes these are also called solvers. You hear about things like SAT solvers, SMT solvers, and so there's a bunch of words, but basically when I use the word reasoning, I mean specifically, I mean something super precise. I don't mean like there's emotion but then there's logic and all this stuff. Like I mean very specifically in the scientific realm that it is the use of logic and knowledge to do things. Whatever the things that it does, that's tertiary, but those pieces, the logic and knowledge, is principally important. So going back to this, this is a stochastic and it has no reasoning. This is really important, the no reasoning part. And then you have over here, you have things that can reason. And if it can reason, it means it must be able to do logic. It has to. Otherwise, it's not a reasoning system based on what we just saw. And in this space, you have things like Jan LeCun's world models, and you have things like symbolic reasoners. You have things SAT, SMT solvers, and then you also have things like diff. Now, what makes diff and world models different than many of the other traditional systems that can reason is that these guys are learned. And these guys are rules-based. So historically, the only way that you would build reasoning systems is through concrete rules that we understood as a species, things like induction, and we would program all of those details into them, and then it could reason about the stuff that you programmed into it, which is cool. Which is great. And it's going to guarantee that it's going to get essentially all the right answers for all the rules that you programmed into it. The problem, though, is that it's limited in what it knows. It's limited knowledge. because the only knowledge that it has is the stuff that you've put into it. Whereas the learned systems is that these things can be massively scalable. That's the fundamental difference between a learned reasoner and a rules-based reasoner. They're still doing reasoning. Both systems are doing reasoning. But one can enhance its own knowledge by learning from the world, and the other only gets enhanced by things that we program into it, that we plug into it. And it wasn't until recently that we learned how to build reasoning systems that could learn. I want to also point out that all learned reasoning systems, this is also a very important detail that is super important to keep in mind, is that these rules-based reasoners, they can be 100% correct. You can verify that they will be 100% correct, and then we call them fully formal. Any learned system, any learned system can never guarantee, not guaranteed, 100% correct. It is impossible. And the reason for that is the things that it learns on is going to be a subset of all of the data in the world. So that's the first piece, is not guaranteed to be able to have the complete data. The second is there's no guarantee that all the things that it's learning on are going to be 100% correct. Now, there's ways to mitigate the potential fidelity of this. You know, you do things like what diff does, which is Byzantine consensus, which is basically you build a consensus system that all these systems have votes, and they all vote together, and then you do like a majority rules, all this, fancy stuff. But no matter how you solve it, it is, once it's learned, it can never be 100% guaranteed. It's not possible. At least to the best of my knowledge, it's not possible. That also means that even though diff can reason and it has semantic understanding, diff cannot guarantee that it is going to be 100% correct. It's not possible. And I have a strong suspicion it's the same thing with Jan's world models. It can't guarantee it. Now, we can get like pretty darn close, but this is a very important distinguishing characteristic, that if you need 100% certainty, like the kind of stuff that they do with formal verification for spaceships and stuff, you may want to do this. These systems over here, that you can get to nines, you can be like 99.9999% correct, but it could still be wrong. And then what we call these is that these are semi-formal. It means they're still based on formality, so they still have a formal element, but it's not fully formal. It's not a fully formal method. It's a semi-formal method, and that piece is from the learned. So you have a trade-off now. Is you need to ask yourself this question of, do you want a fully formal system that has 100% guaranteed correctness, but it's going to be limited in the things that it can do? Or do you want something that is semi-formal, that is going to be able to scale and do a whole bunch more stuff, but it can never guarantee 100% certainty? And this is science, and science is all about trade-offs. And anybody that's trying to tell you something different is probably either confused or they are selling you something. So even with diff, it is not a fully formal system. It's a semi-formal system. But there are major advantages to semi-formal. And most of the systems that you guys use today, when I say that you're writing code And just to make it easier, when we think about code, we can think of it as it's a fully formal system. That's not exactly true. And there are some cases, but in most of the cases of software code, it's actually semi-formal. An example of that is, let's say you write some Python code or JavaScript code, and you have a variable. The type of the variable doesn't get bound to that variable until runtime. So what does this mean? Is that it has variable behavior. That behavior is unpredictable, and it's going to be based on the runtime environment and the input. Therefore, it's not actually fully formal, because the type that you're giving it might not actually work for the function that is doing whatever the thing is. Okay, we've been going for almost 2 hours now. It's awesome. I think we're getting into like the main stuff that I really wanted to get into. I'm super pumped about that. So let's take a short pause here. Yeah, let me look at some of these comments, take another bio break, and then we'll continue one more power through to talk about the big difference of these traditional hacks versus AI takeover. Okay, we'll start with IG. Everything is math. Actually, it's one way to look at things. LMs just predict the next word. But which one the prediction gets to the output can be changed. Yeah, Fontima. Absolutely. The reason why LLMs seem to have sentience or consciousness is because we're trained on the data that has that. Yeah. So, I think I know what you're asking here, Fontima, and I think I agree. So Fontima is asking, doesn't it depend on the use case, just like precision and recall problem? Yes, I think that that's correct. If you're asking about its like the accuracy that it can have with semi-formalism, it depends on many things. If you're talking about code, yeah, that could be the case. But if we talk about the semi-formalism of things like diff and word models, I think it's related to not only domain, but then the data that you're training it on. And just to be clear, I think that the way I'm defining diff is all diff systems they use semi-trust. I think that's right. I have to reference the white paper, but I think I made it a requirement that diff systems must use semi-trust because ground truth is just sort of a broken idea, in my opinion. It's kind of like the Roman numerals. It's like it's a good starting point, but without the number 0, you're just cooked. So ground truth is the same way. It's like it's a neat idea, but the notion that there are not gradients of truthiness in data, you're cooked. You're already done. So there's another thing, and Fatima, you should check out our Discord. I think that, based on your comments, you probably fit in very well. Let me drop a link, but I want to have one more comment on something that Fatima said here on IG. Is he or she is saying that we think that the LLMs are sentient or conscious because we train them on data, and some of that data has relationship maybe to language itself or to humans. There's another reason why that I think is also really important. So I agree with what you're saying, Fatima. I want to just add to this. One of the things that humans do, and like this is well documented, so feel free to look at the research and make your own conclusions, but humans are really good at doing fast pattern recognition and putting things into boxes. Like this is part of our survival for our species, is we see something and then we immediately say, oh, That is this thing. This is part of the reason why I think we can imagine shadows are like, oh, it's this person that's broken into my house. Because we can see this shape, and then from that shape, we can say, oh, that looks like a person, so I'm going to make it a person, and it's not a person. It's just like your coat hanger with a coat on it or something, right? This, I forget the name of this, but it's this, essentially this characterization of things and making them into something else because they have similar qualities. And so I think a lot of times what we're doing with language models is this, is that they have a really great ability at sounding human. It's very convincing. So we immediately transform them into this human entity. And so I think that that's another, there's a specific word for this. Maybe you guys can tell me what this word is. I feel like it starts with a P. Anyway, okay. So, yeah, awesome. So, Phantoma, yeah, I think that we're absolutely on the same page. Okay, so JB's got this really interesting comment. Would chain of thought for LLMs count? Uh, so, JB, can you elaborate a little bit more on what you're asking? I think you're asking, does that put them in the no reasoning category, or does that put them in the reasoning category? Thank you, Alex. That's exactly the word I was looking for. Personification. Yes, 100%, Alex. You nailed it. Yes, that's the other word, anthropomorphizing. Both those words. Yes, thank you, Alec. Those are both the words I was looking for. You are personifying or you're anthropomorphizing. And that makes the language models kind of feel like they're human. Major props, brother, for helping me out. Okay, so for chain of thought, I need to revisit this, but I remember when I was looking at chain of thought reasoning, and as someone that is, like, I'm not trying to be an elitist scientist or anything, but there's certain words that like really mean a lot to me, and I really dislike when people hijack those words. And one of the things that I saw is they would talk about chain of thought reasoning. And again, I have a very, when I say the word reasoning, I mean this. Like this is like super precise. So I remember when I was first looking at chain of thought reasoning and thinking, boy, I'd like to talk to somebody about this term. That being said, I'd have to revisit it because I seem to recall there being something about, at least if I recall correctly, there's something about essentially building out these trees of possible outcomes, which is very similar actually to what formal methods do when you're trying to solve some of these problems, is you actually walk through trees exhaustively. So that's really good. But the problem that I was seeing with the chain of thought reasoners is that without a semantic foundation, you can't actually walk the tree, because you would need to have the semantic understanding of things to build the right trees. And as I recall, like, chain of thought reasoning was basically trying to take the unreasonable language model and then try to help it understand how to do things without building like a knowledge graph, without having concrete semantic understanding of things. So I'm not sure. Let me just actually add this to my list of things. I'll look into this and try to refresh my memory. I'm not even going to write the R word next to this because it annoys me so much. Let's say is logical. Like, for example, it may be logical in the sense that it walks or builds the tree exhaustively, but if you don't have the right foundations, then the trees that it's going to build are not actually going to be constrained the right way. Okay, let's take a 10-minute break. Let me bring up my thingamabob here so I can give us our countdown timer. I may not need 10 minutes, but let's just call this break between second and third act. Cool. By the way, I think if I'm remembering correctly, JB built this. Is that right, JB? You built the assets for this? JB's gone silent. Maybe he's already on break. Okay, so we'll take a short reprieve, and then we'll wrap this up as we get into the scope of hacks and the scope of AI takeover. All right. Do all the stuff. We'll see you guys in 9 minutes. Oh, I need this thing. Okay. Built is overrated. More like scrapped together. Oh. You're so humble, JB. We love that about you. Yeah, JB is a rock star. For any of you that don't know already, for those of you on the Discord, you probably already know that he's a rock star. But for those that are just joining the live stream, yeah, this guy is a superstar. Many skills, many talents, and gets stuff done. Oh, just as additional clarification point, I am moving. So I am selling my current house and I'm moving a little more inland in Cali. Part of that just because it's just insanely expensive. The other reason is I don't really need to be as in the dead center of Silicon Valley anymore because, you know, I don't work at Intel anymore and I can kind of make my own rules. So I'm going to start that process. Actually, we've already started the process, but I'm going to officially move into my rental place next week. And then we're going to put this house for sale and then do all the other stuff. Anyway, the only reason why I'm mentioning it is you may see a small disturbance in the live streams and the VODs for a couple days. I plan to move into the rental next Friday or Saturday. And I actually plan to be up and running, and I want to be doing a live stream the day I move in. Just because it'll be fun. And it'll be a new environment, and you guys can see like a different background or something. But I'll also be able to test the internet and all these things. But from now until next Friday, I might not have as much live time, or I might be a little bit slower on the VODs and clips as I'm coordinating because I've got to just juggle a whole bunch of stuff. Anyway, just wanted to mention this, so if you see a slight delay or slight disappearance for me for a short period of time, now you know why it's happening. Okay. Yeah. Sorry, what are you saying, Alec? Oh yeah, actually maybe what I'll do. No, I don't know if I can do that. Yeah, it is. It's more along the lines of just getting a little bit, because I think you guys know my big plan is I'm yeah, about 100%. My goals are three things: continue to build incredible, awesome tech through some vehicle, whether it's Merly or other things through GTT. Then also doing GTT, because it's really important to me to not just teach the students at the uni that I'm currently affiliated with, because it's too privileged. I don't like it. Not everybody can be here. And I was trained by a whole bunch of people that went out of their way to help me from a distance, like Morris Herlihy, and so I am going to do the same thing. And then the third is that I continue being directly involved with the uni that I'm involved with. Yeah, and the good news is, Amber, and I don't mean this in a like a flexing way or like elitist way, but thank goodness I have people. Is my people help me with a lot of the stuff, so then I can just keep doing the easy thing, which is doing the, running the company and doing the streams and the VODs and then teaching and doing research. So yeah, it is a huge logistic nightmare, and boy, am I glad to have all the folks that are helping me. Okay, so last piece, and maybe what we'll do is we'll just touch on this just a little bit, because we really need more attention to this topic than I think I have the energy for right now. But we can start to tease it out, and then maybe the next live stream, maybe tomorrow, we'll go really deep down this rabbit hole and we'll get into all the differences. But the stuff that we're starting to see, like with the X hack, and have there been other major ones where people have, well, what I think is going to happen with AI takeover, with SLMs being overwritten and the bad actor or malicious SLMs? I think that that's coming. Oh yeah, in all the cases where you see, especially in vibe coding, where the AIs go to do something and then they end up deleting a production database, or they wipe out the entire drive. Or I think in something that I recently heard, it went through and can't remember what the company was, but the AI systematically erased the existence of this software. No, I think maybe it was the customers, is they had all this information in their database, and so it wiped out the database, but then it also wiped out all the history in their repo. So it was like fully wiped, not just like a temporary thing where you have the backups and then everything's great because you have the backups. This thing, I can't remember which AI it was, but it basically did a full systematic erasure of the stuff. It's somewhere online. I think it happened very recently. On the Discord, I'll try to find the link and drop it in the cybersecurity channel. But these types of things, these types of just massive levels of destruction are unique to AIs. That you didn't really hear about this type of stuff with traditional hacks, right? Like, even if you think about the XZ utils backdoor, which was one of the most elaborate hacks I think I've ever seen. The sophistication of it is just, it's brilliant, even though it's super bad. All that did was basically open up a pipe on somebody's machine to then send data. But these things that you can do with the AIs, it's like anything under the sun, and that really has to do with the broadness and the stochastic element of the AIs, because of them not being formal systems that have super rigid parameters. And what I anticipate is going to happen is, until we have strong semantic reasoners, this is going to become a major thing. A major thing. Because there are essentially, in my mind, it's like there is an infinite number of 0 days that they can execute on because of that unbounded structure that they have. And so while I think that, for example, with Grok, they probably patched it in that it has all the crypto types and then it has the give thing. So sure, that will work as a first order pass. But then all you need to do is have another thing that then gets invoked that's not on their hard-coded list, and then have that thing be the thing that does the transferring of the crypto or something else, right? And then on top of that, the reason why this half-baked solution that I'm assuming they have, because I know they don't have semantic reasoners at this level, is it's just a hard-coded table, which doesn't work principally because new cryptocurrencies come into existence all the time. So then as new things get added, you don't have that covered, right? It becomes a maintenance problem. Whereas again, if you understand the concepts of things, then you fix it at the source. You fix it at the heart of the problem. So all of us, I think, should be working with the AIs in a hyper vigilant way. That I'm not in any way trying to encourage us not to use AIs, because I love AIs. I think that they're super awesome, and I really think that language models have tremendous power, and they're enabling me to do all kinds of crazy things that I couldn't do before. At the same time, I think we need to be very careful with the way we use them, because they do have superpowers, and if we aren't proactively careful, we can't do this after it's already happened. We have to have the measures in place before the bad thing happens, so then when the bad thing is happening, it's already in the right container. And the best solution that I have right now in my head is basically sandboxing. And I at some point we need to go through Hostinger and walk through how to do sandboxing there. You don't need to use Hostinger. You can do whatever you want. And if you're an expert and you're very confident that you don't need a sandbox because you know what you're doing, then by all means, don't sandbox. You do your thing. But there are other things that I think are really us moving too fast that we should slow the heck down on, because it's like we're asking for problems. And one of those things is MCP. I have been very hesitant to use MCP because of yes, you can do amazing things, but as Meredith from Signal has pointed out, and I am very much in lockstep with her thinking. She's the president of Signal, the security-minded texting company that many of us use. She, I think, makes the point that a lot of some of the stuff that we're doing with these AIs is basically to turn our brain off. So just give the AIs authorization to do all the stuff, so then we can turn our brains off, and then they can just do all the things. And I don't necessarily disagree with that. I mean, some of us are using it to accelerate ourselves, but some of us are using it because it's like, oh, cool, the AI can handle all that stuff. I don't have to deal with it, and so give it all the privileges. But that's a lot of power, and there's a bunch of stuff that can go wrong. So I guess maybe that's the second piece that I would advise on, is that you sandbox the AIs if you have any concern about what they could potentially do and you not being an expert. And the second is I would strongly encourage that you minimize your use of MCP. I personally am not using it at all. And it's not because I don't understand it. I understand it and I get it. It is very powerful and you can do a whole bunch of stuff. But the risk is I can't have my stuff getting hacked. I can't have certain things that are really high in value, like Merle's IP or something, get accidentally hijacked on some MCP pipeline. But if you want to use MCP, then by all means use it. Just know that it's very risky, and my recommendation is that you minimize it. Like maybe there's something in MCP that you absolutely need to use it for because it's critical to your day-to-day life. I get it. I understand, right? It's like me running Claude Code. I run Claude Code locally. I don't use the web stuff at all, and I'm at risk, but I have a pretty strong understanding of what I'm doing, and it's also reasonably sandboxed, so I'm doing it. So if you have the same thing, then by all means, continue doing the thing, but just try to limit it so only those critical things that you must have it for is the stuff that it's being used for. That other stuff that it's just nice to have, maybe don't do that yet. Because eventually what will probably happen is we will have security protocols that are built directly into it. And by the way, encryption in travel and even encryption at rest is not sufficient in some cases because, well, let's save that for another VOD. But those are my two pieces of advice. And next live stream, I think we'll go deeper into the hacks and AI takeover. And I hope everybody enjoyed this. This was super awesome. I'm going to clean this up and get this dropped onto YouTube for members and stuff. And I'll see you guys on the Discord. So keep going, keep growing.